Okay, hello. So we started the day with surface waves, and we end at least the talks with some impact of surface waves. So this work is part of the TRR, and we investigate frontal dynamics in the oceanic surface mixed layer. And here I will present some results of the impact of wind and surface waves. And I will especially concentrate on inertial oscillations. So how to incorporate the effect of surface waves into a phase average Boussinesq equation or a tendency equation for the Eulerian velocity u. We do that by prescribing the Stokes drift in what is called the Leibowitz equation, which is here given by a mathematically identical form given by Suzuki and Fox-Kemper. And the Eulerian velocity plus the Stokes drift is then the Lagrangian velocity. And the effect of surface waves you can see basically in three terms. So we have the advection term, the Stokes drift is in the Coriolis term, and we have this Stokes shear force, which is responsible for generating Langmuir turbulence. And the Stokes shear force together with the Stokes advection is you can combine to what is called the vortex force, which is more famous. Okay, so surface waves drive inertial oscillations and also what is called an anti-Stokes flow. If we consider the above equation and consider a linear in this case and just imagine that the Stokes drift is just a function of z and of t, if we like, and we just look at zonal Stokes drift, and we are away from lateral boundaries so that no pressure gradient can be established, then the horizontal equations look like this one here. So the Stokes shear force then only shows up in the vertical momentum equation. And if the Stokes drift changes over time, then this generates inertial oscillations. This was already shown by Hasselmann in 1997. And if we go to a steady state, then the Stokes drift is just compensated by an Eulerian flow, which is called the anti-Stokes flow. So if we take the Coriolis force into account, surface waves have no mass transport. It's often not very acknowledged. And it's fundamentally different from the original solution of Stokes. What is totally unclear at the moment is the impact of turbulence on the Stokes drift. So we, as often, we assume that there's no impact on the Stokes drift. So our vertical viscosity only operates on the Eulerian velocity. Okay, so we use a large eddy simulation to show the impact of thermal on balanced flow. So here we have a setup where we have an initial less stratified mixed layer depth of 50 meters on top of a well stratified interior. We have two opposing jets because we have lateral boundary re-entering boundary conditions. Sorry, and both of the jets are in thermal wind balance. So we have a highly anisotropic model domain in the along front direction of only 900 meters, but in the cross frontal direction it is 40 kilometers. And the grid resolution of horizontal grid resolution of 2.5 meters and 1 meter in the vertical. So the minimum Richardson number is 2.2, so that it's stable to symmetric instability in the first place. And the frequency is chosen, or the Coriolis frequency is chosen, so that we have an inertial period of 1 day. And the whole setup is meant to resolve symmetric instabilities, Kelvin-Helmholtz instabilities, inertial shear instabilities, Langmuir turbulence, but we do not resolve baroclinic instabilities because of our short time scale and also of our short along-front domain, which is much shorter than the fastest growing waves. Okay, coming to our first experiment, which is just the forcing is just monochromatic swell waves of wavelengths of 100 meters and an amplitude of 2 meters and a period of 8 seconds. And here on the left-hand side, you see the profiles of the Stokes drift. So we have the same strengths in U and V, but a negative V component, so that the Stokes or the swell hits the x-axis with an angle of -45 degrees. We have no sudden appearance of the Stokes drift, which is often used, but here we have an exponential increase over the first 10 hours, which is, of course, has an impact on the inertial oscillations. And we use the same exponential increase in the first hours as Wagner et al. 2021. So how does the result look like? So here on the left side, you see the time evolution in the Lagrangian Stokes drift, and on the bottom, on the Meillonian Stokes drift. You see that in the first 10 to 20 hours, the increase in the Stokes drift here on top of our two jets. And after that, we see the inertial oscillations, which has an amplitude here of roughly 10 centimeters per second. After about, on the top right, we see the TKE, the turbulent kinetic energy. After about 20 hours, the flow got unstable, and we have an increase in TKE. This increase in TKE is a little bit out of the region of the jets, but dominantly in both of the jets, but not evenly distributed. Might be a bit difficult to see, but it's from the southern jet, it's just in the northern half of the jet, and in the northern jet, it's just in the southern half of the jet. And we see some of these inertial oscillations followed up. The whole TKE is produced or nearly produced by the Eulerian shear production term, which is shown here on the bottom right. And I could also say by the arcgeostrophic shear term, so it does not extract energy from the jet, it extracts this energy from the inertial oscillations. So we have a closer look at the black marked line, so a section on the next page. And it's again shown the shear production term in these colors. And we see this is a jet, or the contours are the Eulerian velocities. This is a jet here, and we see that the shear production term is mainly here up to nearly 30 meters on the northern side of the jet. And we see that we have strong increase in the Eulerian shear at that position. Why is it only here? This can be explained by the effective inertial period, which is just 2 pi over the effective Coriolis force, effective, which is a modulation of the Coriolis parameter by the vertical geostrophic vorticity, as shown by, for example, Morse 75 or Kunze and Sanford 85. And if we look at the inertial periods, there are large differences. So on the northern side, it is just 18 hours compared to our 1-day Coriolis frequency or initial Coriolis frequency, but it's up to more than 50 hours on the northern side of the planet. So this projection here is just because the inertial frequency is much faster on this side. And we have stronger shear. And the overall impact of the swell on the front is here again shown the Lagrangian velocity u. So the overbar is the zonal average, but we additionally averaged over one inertial period, where I have to say that is the time average here is 1 day. It's not the effective inertial period. And we see that the jets are now tilted towards that direction. It's tilted. It is mixed on the right-hand side here, where we have the increased TKE. The momentum is mixed, and we have some subsurface intensified flow. On the figure on the right-hand side is the totally horizontal averaged Eulerian profile and the Stokes flow. And if we average over the total horizontal, not along front, but also cross front, we somehow cancel out the effect of the opposing fronts. And so the right-hand side is the Stokes drift and the anti-Stokes flow. So vertically integrated, they cancel out each other, but as said in the beginning, the anti-Stokes flow is vertically mixed, so that we have no vertically integrated mass transport, but we have kind of an overturning. So the Stokes drift is always larger at the surface, and in deeper oceans, the anti-Stokes flow is deeper. So that leads to this tilting of the front here, and also to this subsurface maximum. Another way to excite large amount of inertial energy is through storms. And this is another experiment, a storm experiment, or an idealized storm, where we just increase the zonal wind stress in the first 24 hours up to 1.0 Newton per square meter, and then we have a linear decrease. The Stokes drift here is now not from monochromatic waves anymore. It's from the frequency spectrum, which is corresponds to a fully developed sea. So it's an equilibrium with the wind stress. Here we chose a frequency spectrum from Alvarez 2003, which is an update of the famous Pearson-Moskowitz spectrum. But we allow for a small delay, which corresponds to some wave growth. So the small delay is 4 hours until it catches up with the wind. So that's the orange line is the surface Stokes drift. And we have 2 experiments, just the waves, and 1 experiment where we force with wind and waves. And this is the time evolution of the buoyancy. The overbar denotes an along front average in depth of 10 meters. So we initially have the 2 fronts here, where the southern front initially, or the initial southern front has the down front wind, and the upper front has the opposing wind. So in the first 48 hours during the time of the storm, we have the large Ekman transport to the south, and the southern front, the initial southern front, re-enters at the northern side. So after the storm, this is the front with the down front wind, and this is with the opposing wind, the southern side. And you also see that after the storm, this experience again strong inertial oscillations. So if we compare the buoyancy sections after the storm at T 49 hours, we see on the left-hand side the wind experiment. So we have some strong mixing through the wind. So the isopypnals are very steep, especially on the southern or in the northern front after the storm, where we have the downwind wind, which experience what is called a positive Ekman buoyancy flux, where the Ekman advection just advects colder water above lighter water, and we have a lot of convective mixing here, so very steep isopycnals and small increase in the mixed layer depths. And the opposite happens on the other front. There will be lighter water advected over heavier water, and the now southern front is much more stratified. If we compare this to additional forcing with the waves, the isopycnals on both sides are much steeper, and much more buoyant water is mixed in the mixed layer depths, and this is simply because of the strong Langmuir turbulence, which enhances the vertical mixing quite a lot. Yeah, and we also have deeper mixed layers because of the Langmuir turbulence. If we split up the TKE production term into argiostrophic production and geostrophic production for both terms, you see in the wind case, very strong, the scale is not even linear, so very strong argiostrophic shear production in wide areas in the wind case, and small and then maximum of geostrophic shear production here in the down on the northern side, the northern jet. The figure is very similar for the wind wave case, but with much less argiostrophic shear production. So this is associated with energy TKE production from the inertial oscillations, and on the right-hand side, this is from the geostrophic flow, where we have negative potential vorticity, which is not shown. So the right-hand side, the energy gain is through symmetric instabilities. If you saw Fraser's poster yesterday, that's the same mechanism, and I guess we will hear tomorrow more about this downwind generation of symmetric instability. So we concentrate here on the inertial oscillation. We have some what we expect at the bottom of the mixed layer. We have some generation or TKE production because of the inertial oscillations, but very strong here in the interior. And this is the reason here is that this is still very well stratified. So if the mixed layer is totally mixed, as in that case, then the inertial oscillations reach, or most of the energy is vertically mixed, and it reaches the bottom of the mixed layer depths and loses some energy to mixing, but a lot of energy into the internal wave field by just form drag. And in the case where we have much more stratification, much more of the internal energy stays here. Okay, that's nearly all. I have no conclusion. I just have something to discuss. So both the largest surface gravity waves and inertial motions are the two largest energy sources in the oceanic mixed layer. And I saw that they are kind of or a little bit related. You can generate inertial oscillations from surface gravity waves, but both are very poorly represented or parameterized in nearly all ocean models. Yeah, that's all. Thank you.